Terminal.
RCP chamber pressure looks good.
Doubling up. Roger roll, Atlantic.
Water towers can fly! Yes!
Tango Delta nominal.
Fighting outside SC off. Bring in SC off.
Yikes. You bet. Concur. We don't need any more of these.
All right, folks. Did the bar move? Yeah, the audio bar moved. You know the drill. It's time for another Intrepid Museum Astro Live. John Galloway here, your host for today. Very special, sort of hot start to the show. No pre-show. We're going to hop right in with the special guests. But you know the drill. Give me some 5x5s in chat. Let me know that you can hear and see what's going on. You're already spamming 5x5s in the chat, apparently. You've seen streams here before. We're going to have some very special guests today. Again, Astro Live, the show that we do with Intrepid Museum up in New York City, an actual museum that's an aircraft carrier that also has a space shuttle and a bunch of cool stuff on board. We have been doing these, you used to call them Virtual Astronomy Live, now we call them Astro Lives, and we do them once a month. It's the third Sunday after the Thursday after the third Sunday, something like that. Just check your calendars and subscribe on YouTube and Twitter and stuff so you know when they are. But that is our plan for the day. We're going to be talking with folks from NASA JPL, the Jet Propulsion Laboratory, about the SWOT mission. I'll let them decode that acronym for you. I guess I could just read on the screen. I put it on the screen, so if I ever needed to explain what SWOT stood for, I could read. It's down at the bottom of the screen. We're going to have live Q&A hopping in with the folks from JPL right here. But really quickly, folks, remember, these things don't just happen. The Intrepid Museum shows are actually made possible through a NASA cooperative agreement awarded to the New York Space Grant Consortium. I'm just going to show that on the screen there so y'all know what's going on. And let's bring our special guests over here so we can get on with the main show. Please welcome our friends from NASA JPL and Summer Ash. How's everybody doing today?
Good, Das. How are you?
We have video and audio from everybody. I see a bunch of videos. I heard some audio. Summer Ash, of course, is going to be our moderator. Margaret and Ben are going to be the folks from NASA JPL talking about SWOT. I will hand it over to y'all. Go ahead, Summer.
All right. Thanks, Das. Actually, I do want a compilation of all the times you've said the consortium throughout all of the Virtual Astronomy Lives.
Sometimes I just put it on the screen, so, you know, it's an accessibility thing.
All right. Hi, everybody. Apologies for my dull background and weird lighting. Last minute change of plans because New Mexico internet is not dependable sometimes. So hello and welcome to our discussion about SWOT, which is the Surface, Water, and Ocean Topography mission at NASA, run out of JPL. And our two amazing guests today, we're joined by Margaret Srinivasan, who's the Applied Science Systems Engineering Group at NASA JPL, and she is the SWOT Deputy Program Associate for Applications. And we also have Ben Hamilton, who is a research scientist in the Sea Level and Ice Group at NASA JPL and studies the ocean with a particular focus on sea level variability on interannual to decade timescales. Margaret and Ben, thank you so much for joining us today.
My pleasure.
Thanks for having us.
Can I start out with my normal question, which is just how did you first get interested in science and engineering, and how did you come to work at NASA and on the SWOT mission? Who wants to go first?
I can go first. So I am a scientist now, as you mentioned, but my background's in aerospace engineering, and my early graduate work really started out looking at satellite altimeters and trying to measure the ocean from space. I thought this is really cool. I know it's kind of a weird shift for an engineer to start working on oceanography and some of these ocean topics, but to really be able to understand this really important part of the Earth, the ocean, which is playing such an important role in climate change, it really started to capture my interest. And just over time, I've continued to work on these satellite altimetry missions, studying sea level. Sea level rise is a big problem that we see along the coastlines. And I think having that societal benefit element to the work we're doing is really interesting. But that's evolved over time. So continue to work with the progression of satellite missions up through SWOT, which we're going to talk about today.
Right on. And have you always been at NASA, or did you do some missions elsewhere before, or you just
Yes.
NASA for life?
No, so I came to NASA from Old Dominion University. So I was a professor there in coastal Virginia. So I got firsthand experience with the coastal flooding problem that we're experiencing along some parts of the U.S. coastlines. I mean, that really did inform part of my interest in coming back to NASA to really work on sea level missions. I'm also team lead of the NASA Sea Level Change team, and that's a pretty big science team made up of people, scientists from NASA, from academia, where we try to come together and use the observations from satellites that we have really to improve our understanding of what's happening along the coastlines and in the ocean.
Very cool. Margaret, how about you?
Well, I grew up in New Mexico, as I mentioned, Las Cruces, New Mexico, and my parents were always very interested in science. In fact, not the first person in my family to work for NASA. My mother worked for NASA when I was little. When I was born, she was working at White Sands Missile Range as a nurse, and she was meeting the Apollo astronauts, and she was just a real Apollo and NASA fan. And so we grew up with the whole NASA, watched all the launches and stuff growing up. And so it was sort of a family culture thing. And also I was interested in science. I just became, through that and just through my upbringing, I became interested in science, and I got a undergraduate degree in geophysics from the University of Texas, and then a degree in environmental and science and policy from Johns Hopkins. And I started out in energy and environmental fields, and then I came to JPL in about 22 years ago. And I came as an applications person to JPL on the Topix, Poseidon, Jason, the altimeter missions, the ocean altimeter missions that Ben mentioned. So and now it's SWOT's the next mission in the series, and so we're very happy, pleased to be speaking about it today, and very, very excited about the mission. It's just going to be an amazing science and applications resource.
Yeah, I bet. So it just launched last month, and it has since fully unfolded. Is that correct? So the instruments and the solar panels, we have a video of it unfolding, I believe. How large is this satellite roughly, the spacecraft?
Yes. So the main instrument, which you'll see kind of unfolding here, this is the solar panels deploying, but the main instrument, the what we call the Karen radar interferometer, which we'll talk more about in a little bit, is about 10 meters long. So the boom is about 33 feet in length. I think the comparison for the bus, that main part of the satellite, is roughly the size of a car. Is that right, Margaret? Maybe there's a better analogy there, but that gives you kind of so you can see the antenna there on folding and deploying. So that right there, which you'll see, is about 10 meters in length, about 30 feet in length.
When it gets fully extended.
Right. So these arms right here, the length from one to the other is about, again, about that 30 feet. So that gives you an idea of the scope there, I think, of the main part of the spacecraft too.
And how many different instruments are on it? You mentioned the interferometer, and there's an altimeter. What else is on there?
Yes. So there's I'll maybe take the first one here, Margaret, then I'll kick it for you. But there's a radiometer that's on there. So when we talk about measuring the height of sea level, you're sending a radar pulse down to space, down from space to the surface of the ocean. And you're essentially trying to track how long it takes for that pulse to get from the ocean and back. Anything that affects how quickly that pulse can move, that microwave radar pulse can move through the atmosphere, matters to us. So in order to get that really accurate measurement of surface height, of water height here on Earth, we need to have a good understanding of that. One thing that causes a delay is water vapor. So we need an instrument, a radiometer, to really measure the amount of water vapor, and then we can correct. Margaret, do you want to take other instruments that are on there?
Well, yeah, of course, there's the Jason class altimeter, which is the nadir altimeter that Ben mentioned. And then there are three positioning instruments, because you have to know the actual position in space of the spacecraft very accurately in order to get these very high resolution measurements. And so there's something called the Doris antenna, which is a European instrument, which is a ground-based radar beacon. There's a X-band. That's for transmitting the data. There's a laser retroreflector array, and a GPS receiver. And so those are the positioning instruments. And then there are two instruments for the transmitting data about the spacecraft, which is the S-band, and then the actual science data to the ground is X-band.
Das, are you going to do some of your Madden red marker magic?
See, the problem is that I can't be like, oh yes, well this is the primary antenna that transmits this, and then this is the, and it, like I know Karen is like, their booms have something to do with that, but what should I circle?
So the first thing you circled is the radiometer, that one that's kind of coming off the side.
Yeah.
That whole bottom, yeah. So that whole bottom area, that really makes up what Margaret and I were just talking about, kind of that orbit determination package, knowing exactly where the satellite is at any given time. And then the nadir altimeter is there as well. But that's where a lot of that. I mean, we already. I'm touching this briefly. It's really important we know exactly where that satellite is and exactly what happens to that radar pulse when it's traveling. So there's all these other instruments, not just the core science payload, that are really critical to have on board and be making those measurements at the same time. And that's really what that kind of bottom of the spacecraft is housing.
I don't know what a nadir altimeter looks like. Is it a thing that looks like a party hat or a thing that looks like a plate?
It's the other dish.
The other dish.
Yeah.
Okay.
It's got the four. Yeah.
So that's the nadir altimeter. I think we've heard that terminology before, right? Nadir, I have heard in reference to the International Space Station. Because the cupola on the space station, the picture window that all the astronauts look out, is always pointing towards the nadir, like down towards the ground. And if you're trying to figure out what your altitude above the ground is, I imagine you would want to point down to the nadir.
Yes.
Excellent.
Yeah. So our satellites, some of the ones that Margaret mentioned, so Topex, Poseidon, the Jason series of altimeters, those are all nadir, kind of what we call conventional radar altimeters. So they're basically measuring a single point directly below the satellite as it's orbiting around the Earth. So SWOT's different because it provides a swath, which we can talk about in a minute here. But traditionally, over the 30+ year record that we have, so Topex Poseidon launched in 1992. Sentinel 6, Michael Freilich, it's our latest nadir conventional radar altimeter launched in 2020. So we have this continuous 3-decade record of these nadir pointing altimeters. That's essentially what it's doing. It's exactly what you said. It's measuring directly below the spacecraft. It tells us the height of the ocean there, and then over time you kind of build up. But yes, SWOT's a big step forward because it's measuring a swath, not just that simple point directly below the satellite, although it does also do that, obviously.
Gotcha. And talking about like doing things over time, you were talking about past missions and altimetry over time. That's what this is, right?
Yeah, so this goes back even further than 1992. So the launch of CSAT, which was back in the 70s, GeoSat in the 80s, and then that Topex Poseidon Jason series. And what this is showing us is just kind of the high definition clarity that we're starting to get as these satellites progress, the technology progresses, and then we're able to see this much clearer view of the ocean. I think it's really interesting too. One thing you notice here is that the ocean is not this flat kind of bathtub, right? There's all this stuff going on. So there's large scale, what we call large scale. So some of you here, Margaret and I are here on the West Coast. El Nino and La Nina have a big coastal expression and ocean expression. So you can see those big features really well. But beyond that, we have all these small scale features. We call them eddies, fronts, currents, all that stuff that our satellites to date have really missed. So SWOT's going to be a big step forward because we're actually going to start to see more of those and be able to understand that finer scale feature in the ocean, which as scientists, we think is really important to understand for a number of different reasons. But it's kind of like putting on high definition glasses or putting on glasses, I guess, for the first time and looking at the ocean that way as you start to look at what SWOT might provide.
Can I ask what, do you know what some of those features are or the reason why there is like the I guess I'm assuming the red, it means higher. Like the heightened things, especially like what looks like at the equator in the Pacific?
Yeah, that's a good question. So the colors on there, in this case, are heights. So the reds, the yellows, and the oranges, those are higher sea level. And then the lower sea level is the purple and the blue. But yes, so this is simulated data. So I'm not going to be able to pull out too many signals, but you see a lot of these kind of coastally trapped waves that go up the coast as it progresses. You see things happening along the equator. So it's all these ocean currents that yeah, they're driven by a number of different things, a lot of them associated with winds, changes in winds, things like that. But you start to get these smaller scale features. But yeah, I mean, there's all kinds of stuff going on. I guess one notable feature, if we want to pull something out for this, you can see the western boundary currents pretty well. So the Gulf Stream off the east coast of the United States, the Kuroshio that comes off of Japan. So some of these really energetic areas, very fast moving currents that have a lot of these eddies and what we call mesoscale. So that's like smaller scale, around, let's say 10 to 100 kilometer size features in the ocean. So you start to see a lot of that variability. In terms of what's happening in the Indian Ocean there, not entirely sure, but there's again, it's simulated data. But yeah, again, it's a lot of these things propagating along the equator, these waves that move in different ways and different time scales.
Those are, I'll just mention that those western boundary currents are really driven by the rotation of the Earth. The Earth is rotating and the ocean is fluid. And so a lot of these dynamics, the very large scale dynamics, are a result of that. And so that's something that we can see very clearly in this kind of data. And but of course, other aspects of what we will now be able to see with SWOT, which are as Ben mentioned, the mesoscale features, simply because there's a lot of exchange between the atmosphere and the ocean that is important for climate and for conditions on land. So there's carbon and ocean heat exchanges between the atmosphere and the ocean, and there's a lot of scientific research on those topics, and that's a very exciting field that I think SWOT's going to inform.
And
yeah, oh, sorry, go ahead.
Oh, I just wanted to clarify. So the meso features, you were saying that's like the tens to thousands of kilometers scale?
More tens to hundreds is kind of your mesoscale. Yeah. And to add to what Margaret was saying, so with climate change happening, global warming, we know 90% of the heat that's trapped by our atmosphere is going into the ocean. So the ocean's been a really big reservoir of absorbing that heat, and it's really limited some of the potential impacts we could see on a global scale because of the warming we're seeing. But the way that heat goes from the surface and then goes into the interior of the ocean and kind of gets spread around, that's where those smaller scales are really important. So those smaller scales help with the mixing in the upper layers of the ocean. And if the ocean becomes less efficient at absorbing that heat, then it has big consequences for global climate change. So being able to understand these smaller scale features, to measure them, to kind of track it along with the heat that the ocean is absorbing is really critical. So in terms of a broad scale global climate change, what's happening to our Earth, I think SWOT's going to fill a really important gap in our observations that we have now and tell us a lot.
Cool. Das, can you bring back up the one that shows the interferometer sending the signals down? Because can you guys talk a little bit about how it's actually mapping / measuring the surface?
Go for it, Margaret.
So sure. Yeah, sure. So what that's showing is this radar altimeter or this Karen radar interferometer system is bouncing signals from the instrument to the arm reflectors, those sort of arms out there reflecting down to the Earth. And those colors, the pink and the green, indicate it's coming from one side, it's coming back to both reflectors, and then it transmits down the other side, and that gives us this sort of I guess parallax view, so that a phase difference when it comes back from the same location on the Earth. And so that provides this view, which in this image is showing the different colors. It's sort of giving us the measurement. And then as this goes around the Earth, every 21 days, it'll see every place on the Earth twice. I think the ball of yarn one that I think you showed first kind of shows how that measurement system will translate to actual data. Yeah. So over the course of 21 days, roughly, more at the polar regions and less at the sort of less frequent at the equator, just because of the fact that the Earth is a sphere. Yeah, that's kind of a good view. So we get a few views of each location that SWOT will cover between 78 degrees north and south, by the way. We don't actually measure at the poles.
Okay. And so how wide is that SWOT swath?
120 kilometers.
Okay.
So it's 250-kilometer swaths.
Got it.
with a 20-kilometer in the middle and then the nadir going down the center. So that's sort of the measurement range.
Mhm.
Here's a graphic for you.
There's one.
Yeah, so the resolution of this is what it does show here, like right there, you'll see that there are some parts that are not covered by SWOT. So if you go a little north of Charlotte where you are, yeah, there are those white spots.
And the open
What would
diamond.
you, because of the resolution of the SWOT visualizer, but you see that's at the crossing points. Some
Like
of those,
those?
yeah.
Okay.
So there are some places where there aren't not measurements. SWOT won't cover every place, but they have algorithms that will then provide a whole, integrated picture of, what we call a gridded picture of that area and other areas.
I use Charlotte because
actually-
I typed in my house, and that's why it's on Charlotte, y'all. No big secret about SWOT or Charlotte. That's just the address I put in.
And no secret where you live. either.
Yeah.
Don't zoom in too far. You'll get.
Yeah. Well, I did do Charlotte, like just downtown. I didn't do like my exact
Okay.
address. This is actually on the JPL website, y'all. It's a web page that you can go to, and you can sort of see how SWOT will swath your area, I guess you could say. Go ahead.
I'm glad you brought that up too, that visualizer, because we've talked a lot about the ocean so far in this here today, but SWOT's going to measure on land too. And with that animation that was showing a SWOT flying over Florida, you can see it's measuring the ocean, it measures the coastal interface where land and ocean meet, and then it's also going to provide measurements on land. So it's measuring our rivers, lakes, reservoirs on a global scale. So I'm super excited as kind of someone working on sea level in the ocean to think about what it's going to do there, but the impact it's going to have in our understanding of water and the availability of water on land is really going to be huge. So it's really the first satellite mission we've had that basically measures nearly all surface water here on Earth. I say nearly all because there's parts, and Margaret already talked about some areas where it's going to miss, but we're really getting this clear view. And Margaret, I don't know if you want to talk about this animation on the Connecticut River.
Yeah, sure. Yeah, this is just an example of the kind of measurement that SWOT will provide over a river. This is the Connecticut River. This is simulated data, and those little brush strokes are various days of SWOT overflights of this river. And the change in color on the river is showing the height of the river. And so if you were to watch it as a progression, it is a flooding event. Mm-hmm. So this is one thing that SWOT will be able to provide for, as it passes over regions that have hydrodynamic changes like this that are significant. It'll show both the aerial extent, how wide these are, and the height. So this is, important for if SWOT is actually flying over and providing data for an actual flood. There are some data products that are going to be available within 2 to 3 days of SWOT overflights, but it'll also input models for forecasting systems. So for future, they can make an assessment of what precipitation is happening upstream, for instance, and then give higher sort of better forecasting and warnings for flooding downstream of precipitation events.
Yeah, so a given pass will give you one measurement, but then will they also average a whole bunch to sort of just get a feel for the average state then of that body of water, so to speak?
Yeah, I think it'll be, in December, this is the average height, in January and February. So yeah, it'll provide a picture over time of what general heights are. And it also, as a result of that, thanks for bringing that up, because it'll also, because this is an example of a river, but this is also true for reservoirs and lakes. And so reservoir and lake storage levels will be able to be measured directly from this. So you can see a progression, a trend of, reservoir levels going down or going up, and the impact of that on, or the relationship of that to, local and regional climate. So.
I've got a question about this real quick. And this may be a super dumb question, but I'm not a NASA scientist. Is this red over here? That means that it's a higher water level, ? Is that what that's showing? Or what it intends to show in this visualization? Is it higher because it's uphill, or is it higher because the water is higher relative to the terrain level there?
Well, what this specifically is meant to show, and by the way, you're not a NASA scientist, but you're a very quick study. I've learned that in the very short time we've interacted. Yeah, so this is showing.
I try.
This is showing an example of flood event. So, in fact, obviously upstream, water, would be higher, and as it goes downstream, it gets lower. And so that, if this were done in an animated GIF, which we didn't do for this visualization, but you might see that flood event sort of pulse down the river.
Yeah, like the flood will move along the river to start hitting other points.
Yeah, that's not exactly how we built this simulated data, but that would be a cool thing to show.
Yeah, that makes sense.
Go ahead.
Oh, I shouldn't talk. You should talk.
I was just gonna say, they're actually, and I'm sorry we didn't provide. There is an animation of sort of a flooding thing. I don't know. It's from if somebody's interested. It's Tamlin Pavelski's group at the University of North Carolina. He's a professor. He's the hydrology science lead for SWOT, and he has done some where they sort of show pulses in, for instance, the Mississippi River and other small river basins, where they show a flooding event that then kind of translates downstream down the basin.
Yeah, it starts out like high up here, and you may see the swelling of the river beyond its normal banks there, and then as that water flows down the hill, it may swell here and sort of recede up here, and then as it flows downhill, it may swell down here and recede up there. And so if it was over, I guess, a shorter time scale, because this is like the satellite flying over and doing one pass, right? Over shorter time scales, you may see that flood going down the river as it expands and contracts. I wanted to point out one more thing here that I thought was really interesting that I hadn't really thought about before. But if you imagine like terrain around a river, right? This is very poorly drawn terrain around a river, and you've got water down in the bottom of the river, right? But you see it change in two sorts of ways. Like you see the altitude of it change, so it goes up and down like that, and then you see it swell beyond the banks. So as it fills up, like the footprint, right, swells as well. The river gets wider and the river gets taller because there's more water in it. And you're seeing that here as the satellite does these other simulated, of course, passes, but you can see the river sort of get more and more swollen, and it's not just swollen, it's also going up and down, right? There you go. There's a good in between the two. And SWOT can measure that from space?
Yes, and that's one of the unique things about SWOT is that it's going to both provide, as I said earlier, aerial extent and height. So that'll give information about another key measurement from river systems that hydrologists are very interested in, which is river discharge. Yeah, that's something that we don't have a lot of information about, or hydrologists don't. I shouldn't say we, because I'm not a hydrologist, but they don't have good sort of ready data on that long term for a lot of places, and this is going to provide that information globally for the extent of the mission. And then not only will they be able to, as I said, see real-time or near real-time events, but they're going to be able to model what actually will happen. So for instance, it's raining this much upstream from this river, and this is what happens. And so someday when there's no more SWOT, they'll have information about what is going to happen, so that it's going to be useful, very useful in models.
We've come a long way from those little posts with the sensors on them next to bridges. Everybody's seen that, right?
Which is still very important. That's a whole USGS system, but that's an aging system, and USGS is one of our SWOT early adopters. That's maybe we can talk about that in a bit, but they're very interested in this for that reason, because this is just going to be so much more data, and they are responsible for that information for at a national, federal level. So
nice.
So with the rivers, and we were talking before just about the mesoscale features, but I'm assuming now that those were ocean specific, because a river is definitely like width-wise is way narrower than 10 kilometers. Sometimes, depending on the river. So like how far down, I don't know how small reservoirs get, but how detailed or how small a body of water can a SWOT detect?
Yeah, I was going to add real quick, there's two modes that SWOT's going to operate in. There's a high resolution mode and then a low resolution mode. So we talked about the low resolution mode, which is over the ocean. That gets you down to like that 10 to 20 kilometer range. But in order to see those features on land, then SWOT will shift to the high resolution mode. So it can see rivers that are about 100 meters wide. So it can see the full extent of it. So like what that animation that Margaret was talking about, you can see the full extent, the length of the river, but it can see those features that are about 100 meters wide. And then lakes and reservoirs that are about 15 acres in size. So pretty small features. And I think importantly, it'll be able to do this everywhere, right, on a global scale, not just here in the US or in particular areas where we already have some measurements, but in areas where we have no measurements at all of lakes, reservoirs, water resources, we're going to have those from SWOT, which I think is really cool. And the one other thing, so Das, you showed that diagram. We've gotten the question, or you drew the diagram, sorry, but we've gotten the question a lot, like how does this compare to, say, what Landsat or optical satellites can provide? So they can tell us about the extent, right, as these flooding events occur. But imagine you drew that same diagram, Das, with very steep sides, right? So you wouldn't necessarily see, as there's more water flowing in a river that has steeper sides or some kind of water body. You would kind of miss how much the change in volume that's actually occurring. So SWOT will actually tell us how volume is changing in these features over time. I should note that SWOT doesn't tell us about the depth, right? So you would need other measurements of the depth of a river, for instance, to really measure a total volume. But by measuring the height change from one time to the next, then you can start to see how volume is changing, right? So imagine you have a cup of water, it's at a certain level, you add water to that, we'll be able to infer the volume change without knowing how big the cup is, right? So SWOT's going to really tell us a lot about how water is moving around and changing over time in a way that other satellites really just cannot.
Nice. And I would assume with the, like mentioning the USGS, that a lot of those rivers, the river beds kind of have a lot of local mapping done already so that they can combine their data with the SWOT data to really get the full extent of potentially a flood or a large water event.
Yeah, local and regional knowledge of that would be useful in that as well. But again, as Ben was pointing out, there are a lot of places in the world where none of that is available. So this will be really important.
Right. Yeah. Das, are you accumulating some questions at all? Or
I am. I didn't tell people that they could ask questions, but tons of people have been asking questions here. And of course, I just ignore them and I ask my own questions because, you know.
Well, can you pick one out while I ask one of my own questions?
Yes, absolutely. You go first.
I'm curious sort of what SWOT would see, or sort of how SWOT would characterize what's happening all in the Pacific right now. And so like with the additional waves, like it would measure the wave height of some of these swells that are hitting California, and then like the measuring of how far inland the flooding is going and stuff like that. Yeah,
it's a really good question. And I preface this by saying that we hope that SWOT will see some of these things. So it's such a new observation that we're going to have to get into and really understand how waves are represented, how swells, and exactly what you're seeing at the coast. But I think you hit on something really important. SWOT is really going to provide important information along coastlines in a way we haven't had those measurements before. So those conventional altimeters, the Topex, Poseidon, Jason altimeters, actually can't get us right up to the coast because of the type of measurement and contamination between the ocean and land. You just get to within, say, tens of kilometers of the coast. But SWOT's going to start to fill in that gap and get us right up to where the ocean starts to meet the land, and be able to understand some of these interactions that can be very small scale. So these waves that are important, these swells that set up that typically we miss. So I think SWOT would provide really important information, maybe not for like real-time response to it, but in terms of improving our models and just our understanding of where water goes when these events like high tides and atmospheric rivers and all this other stuff starts to stack up.
Can I ask also, I have a stupid non-NASA scientist question. How does an altimeter work?
Yes, so a conventional altimeter.
What's the improvement also that SWOT's altimeter has over the previous ones?
Yep. The conventional altimeter, it's not that different than, say, the way a radar gun works, right? A way a police officer is trying to measure your speed as you go down the highway. But essentially, the altimeter is sending a radar pulse down to the surface of Earth, either, here we're talking about water, so interacts with water, then it bounces back to the satellite. So if you know where that satellite is very accurately and how long it takes that pulse to travel to the surface of the Earth and back, and then you can do all these other corrections. I try not to oversimplify it, right? There's a lot of additional engineering that goes into it, but that's kind of the core measurement, right? You're sending this pulse down, you're measuring how long it takes to get back, and then from that, knowing where the satellite is, you can measure height. The reason that SWOT, and Margaret touched on this already, the reason that SWOT is such an advance is because it's measuring a swath, right? So it's not just a single point that it's measuring, it's measuring in kind of 2 dimensions, and it's going to give us this much clearer view of what's happening, and exactly the way that that Margaret was referring to. So it's kind of a completely new technology, same underlying principle, I would say, with some adjustment of you're basically sending a radar pulse down to the surface and measuring what happens to that radar pulse as it gets back to the satellite. But it's really that swath measurement that is the big step forward in terms of what we're going to be able to do in terms of science and application.
Got it. All right.
Margaret, I don't know if you have anything to add to.
Well, I will just add that, as you know, has been pointed out, the data products that are going to come from this are really unprecedented, and so, we're making these measurements. They're brand new. It's a new whole data system. It's an enormous volume of data. It's like seven terabytes a day of data. I mean, it's just an enormous amount of data that's coming in, which is why we have the low resolution over the ocean, just to sort of cut that, and also some onboard processing of that. But so I just wanted to point out that we don't actually know what it's going to look like, but they're all the data system people at JPL and at CNES. We have, of course, partners. We're partnering with the French primarily on this mission, and they're working very hard to get the data out in the next 6 to 9 months, I think. So,
did I hear you say a little bit about onboard processing? Did you just say something like that? Because there's so much data that you kind of have to do a little bit of like reduction or decisions on board before transfer?
Yeah, I'm pretty sure that's just in the low resolution, just over the ocean. Is that right? Is that right, Ben?
That is correct. Yeah. So I think I might have these numbers a little off, but I think that in total it collects about 60 terabytes of data a day, and there's no way to send all that back. Right. So yeah, a lot of the processing of the low resolution data is done on board and then sent down just to reduce it in size and make it manageable.
Yeah. All right, Das.
All right. So y'all asked, and we always take questions from people. If y'all have questions, tag us in the NASA Spaceflight chat, at NASA Spaceflight, or just put your question in the Facebook or wherever. Like, I'm looking at all the different places for questions, but I have a ton, like a huge stack with a little teeny tiny scroll bar on it of questions that have already come in. And a common question is, how does the sensor, how does the device know the difference between water and land? Like, does the radar bounce back differently, or it scatters differently or something? Like, how does it know it's not bouncing off of dirt versus a river? Whoever, I don't know who could best answer that one.
Yes. So, or Margaret, I'll go first. So I mean, in terms of
stab at that, that's a good question. It's a very good question.
Yeah, I mean, in terms of the raw observation, this is going to sound a little ridiculous, but the satellite doesn't know, right? I mean, it's measuring, it's consistently sending down these pulses. You could see that Florida example where it's measuring across the coastal interface, where you start to go into land, but the measurements that get returned are quite different, right? And including what we see with the radiometer, some of the corrections that are being made as you get this return coming back. So yes, based on the observation, our ability to process it and what the observation is telling us, then we can certainly tell the difference between ocean and land. And you can kind of think about how land and ocean appear differently, right? Just in terms of the roughness of it, and the potential return that you get back from it. So yeah, I think that's maybe a roundabout way of answering the question, but we can tell the difference because of the observations that are being collected.
Is it like,
I just like that.
Go, Margaret.
I was just going to add 2 points, which is there's a major effort on the part of the science team that has been been working for over 10 years on developing systems for SWOT and trying to understand what it's going to do, what it will be capable of, and they've developed what we call a land mask. So they actually have sort of cut out parts of the Earth. So in their processing, in that big black box, which I'm going to try, they basically know what not to call water. there's also, you know, a reflective thing. There are some places, I guess it wouldn't be, you know, for the nadir altimeters,
Right.
which don't use a land mask. They actually, you know, for instance, on some deserts and on Greenland, it actually will get a signal that's a valid signal over some land areas. And for an ocean altimeter, that's pretty remarkable.
Right.
But I don't think that's the case with SWOT, because I think the land mask just cuts out areas that are not of interest.
So it like combines with other data, and you get back this information that's sort of just raw information. Like imagine just reams and reams of numbers, right, that are coming off the sensor, and you combine that with other stuff you already know to figure out, all right, normally the land's here, and that's probably still land. And if you see fluctuations off of what you might think should be there, that could say, okay, well, that changed a lot. Either somebody filled in a lot of dirt or the water rose because it's flooding, like things like that, right?
Yeah, I think the mask. Go ahead.
Go ahead.
I was going to say, I think the masks. So, for instance, just take, since we looked at the Connecticut River, you know, a mask wouldn't go right up to the edge of the river, because then if there's a flooding event, it would cut it out. So they would probably have a wide area. And so that's where, you know, when Ben was talking about, you can tell between, you know, what happens to the signal between water and land. You know, that'll be discernible by some very, very complicated math.
Gotcha. That happens a lot because you
get
the,
I understand.
Yeah, you get the raw data back, and then you said product earlier, and it's taking that in the raw data that comes off the satellite and turning it into information by processing it and doing math on it and using combining it with other things you already know, and then all of a sudden you have this product that is this graph or chart or series of numbers or whatever it is that's been massaged into a usable format. Does that make sense?
Yeah,
I think that makes sense, right? That's a data product. Let's see here. Go ahead.
Imagine, or I would think maybe that there's also some sort of code that might spit out ones that might be questionable. Only because I'm aware of the fact that we live in the unprecedented times and there's probably more coming. So you would want to like know if some area just got washed out, even though normally it would be there, but it's some catastrophic thing happened that maybe we didn't notice because it's not a place in the world that, you know, like very, very remote or something like that.
Gotcha.
I don't know.
This is sort of like along the same question here, right? But it's people talking about plastic in the ocean, and we've seen these pictures of big, like continents of plastic or whatever, huge groups of plastic, I guess. Does SWOT see those? Is there something about trash that may be in the ocean that may reflect that back? And you're like, what's this? There's an anomaly in our SWOT data. Is that something you were expecting to see?
Yeah, so I have not heard any discussion about that, but just to think about it now on the fly, I mean, the effective spot size over the ocean from SWOT is still quite large. So, yeah, another way to think about this, when you send a radar pulse down to the surface of the ocean, how rough the ocean actually is will impact how that gets sent back, or how it gets reflected by the surface of the ocean and sent back. So from altimeter measurements, we can actually get an estimate of sea surface roughness, for instance. Like we can tell there's big waves happening if it's a very rough ocean versus very flat ocean. I wouldn't expect plastic to be a big driver of that, or even really large enough to impact the spot size of it.
Gotcha.
And in addition to that, that plastic, I'm not an expert on plastics, but if plastic is floating in the ocean, it's also going to move up and down according to what's happening underneath of it, right?
Yep.
So you're still going to get these measurements coming out of these areas that might be covered by pollution or other things like that.
Gotcha. Makes sense. When they say there's a mountain of plastic in the ocean, it doesn't mean that it sticks up above the ocean. The plastic still sort of rides the waves and stuff like that. So it's not going to be like a huge altimeter difference when it's measured by the altimeter on the spacecraft.
Yeah, well, and a lot of times we talk about the change over time, right? So it's not just like the height at any one given time, but it's how it's changing from one to the next. So if that plastic is always there, then you're not going to see it from one change one pass to the next.
Gotcha.
But one thing about I'll just add about the altimeter emissions, of course. So one of the things that they see are the currents, and sort of areas where currents converge in the ocean are known places for plastic islands, as they call them. And so, you know, what the traditional altimeter emissions for the past 30 years and SWOT in the future at a higher resolution will see these convergence zones, and they will be able to track better where they're, to that degree. They won't, as Ben indicated, I don't know about them actually seeing the plastic or any effect of it, but it'll be the whole convergence where they are already known to be can be monitored.
So back to this sort of imagery, when you see these areas where the ocean is swirling, you might be able to guess where things might collect because you know the motion of the ocean. I think I've said that twice now in this stream. I'll stop.
Yeah.
Well, these are
Yes.
surface currents, and the convergence is sort of surface and deeper as well, right, Ben?
That's right. Yeah, but I was going to add that there's potential uses of this data for, say, tracking debris. So like the big tsunami in 2011 off the coast of Japan, which brought so much debris across the Pacific Ocean. We can use altimeter data to help kind of track and understand where that's going. Oil spills, another one. So may not be able to see the oil spill directly, but you can kind of track the currents and see how it's moving.
Would it detect like a tsunami or the big volcano that erupted and created the wave out from that? Would SWOT pick that up if it were flying over whenever that event was happening?
Yes, so that's actually a big part of my PhD was using altimetry to find tsunamis in the ocean. So you kind of have to get lucky because tsunamis travel very quickly in the ocean. They are large scale, but you kind of have to have an altimeter, including SWOT, in the right place at the right time. But the 2004 Indonesia tsunami was very well captured in the ocean by altimeters. So we actually have pretty good measurements of some of these events. So yes, if SWOT happened to kind of be in the right place at the right time, then it would see tsunamis. And with the SWOT measurement, it actually increases the likelihood you'll be in the right place at the right time with SWOT. So that's cool.
Because you've got just a wider area that you're looking at as opposed to one little pinpoint thing, right?
Exactly, yeah.
But that's still... Go, Summer, go.
Sorry, I'm very curious about rogue waves. Does that mean it could potentially pick up those as well?
It could, yeah. I saw some recent reports about rogue waves, and I'm actually curious to see if any of our altimeters have picked that up. But yeah, I mean, like with the tsunamis, it's in the open ocean. It's not that large, so they can be about 1 meter in amplitude in the open ocean. But that really stands out relative to the other signals that we see. And again, they're kind of fast moving, and with models, we know where a tsunami wave should be at any given time based on when the earthquake or whatever onset factor actually happens. So it would be interesting to see. I don't know of many, Margaret, maybe you do, of any studies that have found rogue waves in altimetry data specifically, but they might be out there.
Yeah, I'm not aware, but yeah, obviously they're much larger than that. So in principle, it seems like it might be possible.
Yeah, I think that's an important distinction to make about how SWOT works, because we think of it and, we have like a discoverer out there taking pictures of the Earth and we use our eyes and we look at the whole Earth at once, right? But SWOT doesn't work that way. When we talk about these swaths, it's winding that ball of string around and around the Earth, and then it puts that all together. But it's not flying over the entire surface of the Earth all at the same time. It's flying over one little section of the Earth, and it's measuring that one little section and recording it. And that was this illustration we showed before. But this is sort of what makes it difficult to capture things like tsunamis or rogue waves or whatever, because at any given time, the satellite is flying over the Earth, but it may not be flying over that part of the Earth. And it's really that over time, piecing all those swaths together and all those passes together that you make this one sort of mid to longer term view picture, as opposed to, wow, right now this is happening in the Indian Ocean or whatever, right? I think
go ahead, Margaret.
I was going to say, it's just that, for measuring a tsunami or a rogue wave, it would have to be just over that one swath.
Yep.
It'd be very opportunistic. I don't know, Ben, go ahead.
Yeah, I was going to add that that complete view of the ocean happens every 21 days. So the repeat orbit of SWOT is 21 days. That's where you get an image or a measurement of everywhere on Earth. I should say almost everywhere on Earth every 21 days. And then Margaret already mentioned this, but some locations will get measured more than once every 21 days, just based on the latitude. So sampling at higher latitudes is better than at near the equator.
Right.
Just based on, again.
It's less Earth up there, and it sort of hangs out as at the top of the orbit, right?
And there are also a number of places around the Earth where they have CalVal, what they call calibration and validation sites, that are right under the track of the satellite. And so at every pass, they recalibrate. So that's an important component of that very complicated math that I mentioned.
It's almost like one of those USGS markers for the satellite. Like it's a spot where they know this is the altitude of this specific spot, and the satellite flies over it. And when it measures that, you're like, hey, you're off a little bit. Fix yourself. Like roughly. Summer, go ahead. Sorry.
So,
Oh, no, I was going to ask, yeah, are those are just points that we happen to know, or there's an actual piece of hardware there that is sending what location it's at to the calibration?
yeah, they're actual sites that are set up as CalVal sites, permanent locations for this mission. I don't know actually if they're the same ones that have been used for the altimeter missions, but probably, or I don't know, Ben, maybe you know.
I think they are, and also we do comparisons back to tide gauges as well. So we have tide gauges along the coastlines of the world. So a check against some of the really good tide gauges we have in different locations, the comparison between altimetry data and tide gauges tells us a little bit about how good those measurements are at any given time as well.
Oh, cool. When you mentioned the sea roughness, does that mean SWOT would also pick up like in the Sargasso Sea, big conglomerations of the seaweed, or would it pick up things like the whole red tide or whatever in the Gulf?
I don't think so. So I mean, when we talk about roughness, it's usually more rough than that. So it's kind of wave size on the getting up to tens of centimeters, that kind of thing. So yeah, actually, to go, not to keep bringing it back to my PhD project, but it was actually funded by the Navy, and the idea was that submarines moving under the surface of the ocean would have a roughness signature on the surface. So they would change the roughness, and you would be able to essentially measure from an altimeter or from a satellite that there's submarines moving under the surface. That never really worked out, but the same kind of principle allows you to go in and look at tsunamis, because tsunamis affect the roughness, have an amplitude, all that stuff. But at least the Navy thought that we could pick out some really small scale surface roughness features with altimetry. Kind of remains to be seen if that's the case. But when we talk about surface roughness, it's usually larger kind of wave size effects.
So maybe like 2 generations of altimeters later, the Navy will get what it wants.
What they want.
Maybe they already have it. I don't know.
That's
Or
true.
airborne.
They're not going to tell us.
Airborne.
Yeah.
Yeah.
Let's see here. There's so many great questions over here. A lot of people are very interested in this, talking about like, oh, well, an oil spill might change the wave height of the water, and would SWOT be able to, like, there's so many questions. Here's one that I want to hit. You mentioned a little bit about SWOT in disaster mapping, I guess, floods or hurricanes, but are there any specific plans? I guess it's hard to have specific plans for a hurricane. Like, who plans for a hurricane, right? I guess you should plan for a hurricane. But is there anything like SWOT is flying where it's going to fly? It's measuring what it's going to measure. It's not like in the movies like, oh no, hurricane over Florida, task SWOT to measure the flooding. Like, that's not how it works, right?
That's right. Yeah, it's in its orbit. We're not going to be moving it. So we've shown that ground track a few times. That being said, I mean, the science mission of SWOT is 3 years, and given the sampling and that swath measurement, I think we should expect to get observations of coastal flooding, of the storm surge associated with hurricanes over the course of its record. And I think even sampling one of those events, I think, will be really important to improving models and understanding a little bit more about how they move in the ocean and how they interact at the coastline. So yeah, it's not going to see every event, and we, like you said, we can't task it to do certain things,
right.
But I think it will provide really good information for us to improve our understanding, which can then be given to those coastal communities to help prepare.
Gotcha. There's not like a go ahead.
I was going to say, this also sort of brings it back to this topic of ocean heat content. So one thing that the altimeter missions do is they provide the surface height, which correlates to the ocean heat content, for instance, in the Gulf of Mexico. And so if you have a hurricane that is going to pass over a warm core eddy, say, in the Gulf of Mexico, that's like fuel for the hurricane. So
Yep.
SWOT will be able to provide that information at a higher resolution, presumably, and to the degree. I think there are people I know, because I just met somebody at a meeting who's a PhD student working on ocean heat content for hurricane mapping.
Yep.
And for SWOTs.
So if people want like the real-time monitoring of things like this, maybe we need like 20 SWATs or something. You know, we can put 18 billion internet satellites up there. Why can't we put up, like 10 SWATs?
Exactly. What comes next?
Yeah, what comes
Once
next?
we fingers crossed with SWOT, everything goes well, then those
two.
conversations will happen.
That's actually one of the questions that's in the queue here. This happens all the time. It's the way we sort of build and launch satellites and missions to Pluto and all this sort of stuff, right? But is there anything that would be useful to have on SWOT 2, like another instrument that could be added, or more bandwidth, or if you had a magical SWOT fairy wand and you could just grant magical dust and make SWOT 2 whatever you wanted, what would you add to it? Let's start with Margaret.
Well, I might add something that would provide more near real-time data, because we have, I work on the application side, which is, people who are decision makers, for instance, and they, data that comes in every 21 or 45 days is not that useful. 2 to 3 days, way more useful, hours to a day, more useful still for some users, not all users. There's a wide variety of people who are going to be able to use SWOT in its current plan.
Right.
But I would say, some black box that makes the data available that much faster would be very useful.
Like a really quick follow-up, is it like SWAT's flying all around the Earth constantly and it's gathering data, and then it like flies over a station and it downloads everything from the last 3 hours or something? Or does it save it for days? How often is it constantly sending data down?
I'm not familiar enough with the data system to say much about that. I know
Gotcha.
that they have.
Yep. It is downloading data or sending data back to Earth every day. I don't know the amount of that, but typically you're not going to store that much on the satellite. Just that,
Yeah, gotcha.
Especially the quantities that are needed here.
Talking about the science data specifically, yeah.
Yep. And then the other, I guess, workflows that get that data into hands that can use it, like some things can be improved there so y'all can get to the data more quickly, I guess. Ben, what about you, SWOT 2?
Yeah, you already teed this up for me a little bit. I mean, it would be a constellation of SWATs, right? And I'm not going to say 20 as you threw out there, but maybe a couple. And the reason for that is that we're going to get improved spatial resolution with the satellite, right? But it's the temporal resolution that's still going to be somewhat limited. So we are going to miss things that are really important. Certainly, we're going to see floods that are occurring, see features in the ocean that may be short-lived on occasion. But if you had a constellation of these, you would really increase the opportunity to see these more frequently. And that's really the underlying objective of SWOT, is to be able to understand these smaller scale, shorter lived features, and both on land and ocean. So I think that would be a big step forward. And then I guess the other thing, again, you mentioned this already, but is it possible to have a satellite that could be not tasked? That's probably too strong of a word, but if we could point it towards the coast, focus on these coastal areas when you're making these observations. Again, that's a lot of where my interest is as we start to think about increases in coastal flooding that are going to happen. But I think that's kind of the direction forward after SWOT, once we kind of see it's successful.
It's one of the things that I always, and people will probably go after me in chat because of this, but when we have science missions, it always seems like we build this one free-range, grass-fed, artisanal satellite that's very specific to its one mission, and then we launch it, right? And it's like, congratulations, you flew by Pluto, like one time, right? When it's a commercial mission, the commercial companies are over here just throwing satellites up like crazy, like, I don't know, I'll take 1,000 of those, launch them, right? And it never happens that way with our science missions. I wish that some of our science missions would say, wow, this SWOT instrument is a fantastic thing that's going to allow us to track these important things about the Earth. We've designed it. Let's launch 10 of them. Let's launch 15 of them. It always seems like, okay, there's one SWOT up there. Good job, little SWOT. You've got 3 years. I hope that the advances that we have in technology and maybe decreases in launch costs allow us to launch more or get more coverage out of science missions. Because we always design this thing once and we build it once and then we launch it once and we're like, good job. It is a good job, but what if we could launch 5? What if we could launch 10? Am I crazy?
No, you're not at all. NASA really is a science and technology development organization.
Right.
And when it starts saying, yeah, this works great, let's do 5 more, that becomes operational, and that's no longer specifically NASA. I mean, we have, we've had a series of altimeter missions. Jason 3 is actually a NOAA-led mission,
right?
Because NOAA is the operational organization for the federal government in the U.S. It's not quite the same at CNES. It's not. I don't think it works quite that way. But so the idea is that we then provide this technology to private sector companies and operational agencies in the U.S. to take that technology, and then we can move on to the next big thing.
Yeah, I will say so. Dallas, I think you're hitting on an important point here, and SWOT I think is a little bit of not a paradigm shift. I mean, it's in terms of technology, it certainly is, but I mean the potential societal benefits that Margaret and her team work on with SWOT is a step beyond what we've seen with some of our other altimeter missions, right? The potential benefit it's going to have to people who monitor water resources, who are living in these coastal communities. I think we're going to increasingly see that as climate continues to change, impacts worsen, that people are going to become dependent on these measurements, right? They need to monitor what's going on. They need to understand. So as that happens, I think it's critical that steps be taken to ensure that 3 years from now, people really like the SWOT data and have it within their workflows and depend on it. All of a sudden, it's not there, right? Not to say SWOT's only going to last 3 years. Hopefully, it lasts longer than that. But
it's from JPL. Come on,
yeah.
It's gonna be 30 years.
Yeah.
No promises, but yeah, I mean, we don't want to pull the rug out from under people, right? Especially as floods worsen, droughts worsen, and flooding starts to increase. So these discussions, I think, are happening. I think NASA is interested in making the observations and the science that we're producing useful for society. So yeah, I mean, I think it's an important topic to start to think about what comes next. And how do we continue to sustain what are very useful observations for people?
Yeah, it makes a lot of sense because what's the market? Like, somebody's got to pay for it, right? And every now and then you have to have funding for the mission, and whenever it goes into a commercial sort of thing or an operational sort of thing, that may mean that there's a market for that data out there. And I hate to think about it like, oh, we've created our own market because of the way that the world is changing, and now we need this stuff, right? But that very, very well may be the reality of the situation. So that I'd never thought about it that way, but that makes really good sense. Like, it moves to operational. NASA focuses on building the next cool thing, and then if there's an operational need or an operational market for it, someone else is going to be out there not doing the boring work but doing the operational work of keeping go ahead.
The expensive part is to develop the technology. So once it's known, then it can be, that's NASA's, one of its missions is to move stuff into the private sector so that it can, it's not like we want to keep all of our technology secrets. It's not that, it's the opposite of that.
Right.
We want to develop this technology, and there are just countless examples of SWOT, of NASA data going out, or technologies going out and into the, probably 8 things around us right now are as a result of NASA technology.
So. The spin-offs office. I think we've done a stream with the spin-offs office before, and it's the part of NASA that talks about how they get these new technologies into the hands of people, or the data into the hands of people. There's an entire whole thing about that. So how you doing, Summer?
Along those lines, I wanted to ask Margaret a bit more, because you're on the side of the applications. What kind of tasks or what kind of things do you do in your job to execute that? Like, are you meeting with the actual users at universities or research institutions, or are you advertising to them what SWOT will provide, or how does that work?
Yes, we do that. So we have been starting the applications task for SWOT started in about 2012. And since then, we have spent time engaging user communities that are not traditionally research entities. Okay. So definitely university, some private sector. We have some NGOs. We have a lot of international. What we have is called the early adopters, the SWOT Early Adopter Program, and you can look that up on our website. And we have 25 right now, and there are organizations and individuals that we have engaged over the course of the last 10 years. And they are using simulated data provided by the SWOT project at JPL and at CNES. And so we have simulated data products so that they can take this data, and understand, so we did a lot of training at first to say, okay, here's what SWOT's going to do. Here's what it's going to see. Is this a good fit for your organization? And so we find organizations that think, yeah, this is a good fit. Yeah, I can see how this is going to help us. And then we help them get the data product in general terms, in general format, into their operational system. So that's what we're in the process of doing now. Their objectives vary widely. We have people who are looking at flood forecasting, for instance, in Bangladesh and in India, and Thailand. We have people looking at reservoir monitoring. We have a early adopter in Texas that it's the Texas Water Development Board. It's a state organization, and they're very excited about SWOT and how it's going to help them measure. They've got 7,000 dammed reservoirs, for instance, in Texas, and only 2% of them are gauged. And so SWOT's going to be great for that. Information about transboundary rivers, river commerce, and marine operations, coastal zone management. And so, we have spent a lot of time sort of engaging with this community. We do trainings. We have what we call hackathons, where we get down in the weeds with their systems and our simulated data. And we're all very excited about getting actual data into their systems. And so that's one mechanism. And it's not just a SWOT thing. We have NASA Applied Sciences, which is what funds a lot of my work for this, has this for a lot of new missions. And so this is sort of a mechanism for bringing people in.
Very cool. Gus, I see you looking at multiple screens.
I am looking at multiple screens. Well, I'm getting more questions, and y'all know when I'm reading the questions and trying to find things, y'all are talking about stuff, and I don't want to be over here on camera looking at this other monitor. Sometimes when I disappear, it's because I'm getting more good questions, and I've got one teed up here. Somebody was asking about Karen, like the name Karen. Was that an acronym, or is it pronounced that way? But that is actually kind of an acronym about the technology that the instrument uses, I think.
Yeah, it is. It's an acronym. So it's the Ka band radar interferometer. So that's what it stands for. And the Ka band is kind of the wavelength that it operates in. So that allows us to see through clouds. That's another thing I mentioned, that we have other satellites that can look at extent of, say, rivers in the optical. But if you have clouds, things like that, you can't see through them. But with this kind of radar technology, we can see through those clouds. But the Karen does come from is an acronym.
The acronym. That's why I turned my camera off, because I want to get the answer, and it's like looking over here and then Googling it and then getting the page to show. Go ahead, Margaret. Sorry.
Actually, there's an interesting sort of corollary there, or an interesting aspect of that, which is the guy at JPL who developed this instrument at the beginning. His name is Ernesto Rodriguez, and his wife's name is Karen. Not spelled Karen, but Karen. But so that's sort of a cool little tidbit of information when you think of it.
That could get confusing. It's like, I'm just over here spending time with Karen. Like, wait, are you working or are you at home with your wife?
Because I'm a radio nerd, I'm just going to add to the conversation that's a roughly 27 to 40 gigahertz, which is somewhere between 5-7 millimeters to 11 millimeters wavelength.
All right.
Who wants to know?
Let's see here. We talked about earlier that SWOT flies all over the Earth. It's not like we launch a satellite and it just covers the United States and we turn it off the rest of the time, right? It can get this sort of data from oceans and bodies of water worldwide. Are there agreements in place, or is it like a website where people can go download it so that folks in other countries who have use for this information can access it? Tell us a little bit how that works when we're sharing this information outside of JPL or the places that you work directly with.
Yes, so the data is all publicly available, right? So as it's collected, it gets put out through different repositories, and anyone can go and work with it. One note on that. So right now, SWOT is in its kind of checkout, calibration, validation phase. So for the first 6 months, it's going to be actually in a 1-day repeat orbit where it's doing really extensive calibration, validation, making sure we understand it. At 6 months, it's going to shift to that 21-day repeat orbit, that science orbit. it'll start collecting data within that science mission, and then shortly thereafter, it'll become publicly available. So hopefully nobody's going and looking for the data right now because it's not available. But yeah, in the coming months, it will be. But I mean, I think as part of those hackathons and the work Margaret was talking about, maybe you can touch on this. I mean, efforts to make that data more accessible and more readily usable are underway within the SWOT mission.
Yeah, NASA has data center that's charged with distributing the data. It's called the PODAC, PODAAC, and that stands for the Physical Oceanography Distributed Active Archive Center.
Impressive.
So the ocean DAC, as we say, there's a land DAC, there's an ice DAC. Different centers at NASA have these, but JPL has the ocean DAC, PODAC, and they're going to distribute SWOT data. Our partners at CNES have their own data system that they're going to be distributing as well. It's the same data. It's going out. And PODAC is developing tools and systems to make this data. It's going to be available on the cloud because there's so much of it. It used to be a model where you would. Actually, when I first started JPL, you'd send out CDs to people with data from, because I Jason one back in the day. But now it's all going to be available on the cloud just because of the data volume. You could previously download it from a data source on the PODAC website. But anyway, it's going to be on the cloud, and there are various formats of it, and that's also true for CNES data distribution. And so, yeah, as Ben said, it's going to all be available for free, and you'll be able to subset it. PODAC is also developing tools to help train people on how to get data from the cloud, and also how to use data from SWOT and a number of other missions. Of course, the PODAC does all the NASA data ocean missions.
Gotcha. I'm trying to remember. What did a CD hold? Like 650 megabytes or something like that? Like 600 or something. Can you imagine, like, if you needed to get some data, you would put 600 megabytes of the data on I can't even grab a CD. There's none around here. And you would put it in the mail and you would mail it to someone. Like, people watching, can y'all even fathom what it was like to share data that way and how far we've come where, just get it off the cloud. It's only 600 megs. Like,
yeah.
Oh, let's see here. I'm still getting lots of good questions. I get to grab new questions and bring it over. Yeah, I don't think that JPL is tracking how much water is in your swimming pool, right?
It's not big enough.
It's not big enough.
Well, someone might have it
really big.
If you have a swimming pool that big, you deserve to have its level tracked. How about that?
Exactly.
Exactly. Especially if you're in the desert.
Especially if you're in the desert. Nice. Do y'all, this may be too much of an engineering question. Do y'all know what's limiting the lifetime of SWOT? Like with satellites, it's sometimes how long a sensor will last or how long the orbit will last. Most of the time, it's how long the fuel will last to keep the satellite in the proper orbit. Do y'all know what the 3-year limiting factor for SWOT is?
I don't know specifically. I think that there is enough, say, fuel on there to last beyond 3 years, certainly to do any kind of orbiting corrections that are needed. I think that's just kind of in terms of the requirements. I mean, obviously with every mission, we have very strict engineering requirements. So It's built to at least last that long. That's kind of the baseline success. So, yeah, I don't think there's plans for anything to fail at 3 years or to break.
It's like the JPL warranty period, right? It's like, all right, it's going to go for 3 years, and then the warranty's up. It may keep working after that, but
it's a good way to put it.
Talk to the JPL warranty, the famous JPL warranty. Let's see here. We talked about the bandwidth some. Y'all, I see some of the same repeat questions that are coming in. And earlier we've talked about the bandwidth and how it downloads things and that sort of thing. We talked about the acronym. We talked a little bit about the ocean temperatures, but the satellite isn't directly measuring ocean temperatures, right? It's more inferring or providing data that can help you get to ocean temperatures. Is that correct?
That's right. Yeah, I mean, there's a pretty direct link between the height of things in the ocean and their temperature as well. So if you think about kind of long timescales, climate change driven things, so as the ocean absorbs heat, that 90% of heat that gets trapped, it expands, so sea level goes up. So we can see that relationship that way. But same thing with these smaller, we showed a lot of those really small scale features in some of those animations. Typically the higher sea levels are associated with warmer waters, and there's consistency there between how things are moving around and the different types of variables that get communicated.
Right.
With the height and the temperature, would that also eventually tell you anything about like salinity or concentration of?
So height does, yep. That's a really key part of another key observation that's complementary to the sea level piece. So anything that affects the density, let's say, I mean, that then affects circulation, affects sea level height, and that's driven by temperature and salinity changes.
Yeah. Okay.
Gotcha.
And the ocean conveyor belt, that's really a deep feature, right? Not a surface one, or are there proxies on the surface for that?
Are you talking about the kind of
Global.
what's happening on the East Coast?
I'm talking about like that global ocean conveyor belt thing that's
Yeah. I mean, so typically there's a surface expression of these. So there's water moving at the surface, as well as a part of that conveyor belt that's at depth as well.
Huh. Let's see here. I think we can answer this one, but somebody was asking about the polar caps. The orbit of SWOT, it doesn't ever fly over the poles, right? It's in sort of an orbit to maximize its time over the bulk of the landmass where all the inland water and that sort of stuff is. But it doesn't fly over the poles, so SWOT isn't going to be scanning snow and ice at the poles, correct?
That's correct.
That's correct. Yeah, 78 degrees north and south. Sorry, go ahead, Margaret.
78 north and south latitude. I was just
so SWOT could be helpful for sea ice potentially at latitudes a little bit lower than that, because again, sea ice kind of comes and goes during the course of a year. You have open water, you have sea ice, and understanding where you have more open water that SWOT can measure can tell you something about how sea ice is changing at higher latitudes. So it does have some relevance to what's happening with the ice, just not those direct measurements that'll consistently stack up.
Gotcha. Real quick, y'all, I think we can illustrate this. I just brought up Google Earth. In the orbit of SWOT, this isn't exact. This is just me drawing it by hand. But the orbits, okay, thanks. Just fine. Go to the other screen. Like I said, the orbit of SWOT, okay, good. It's going to let me draw, is sort of like this, right? And it's not a polar orbit. It doesn't go straight up and down, but it has sort of a maximum latitude, like up here, that it gets to, and a minimum latitude that it gets to. And that's why we said it crosses over those high and super low latitudes more often. When I said it sort of loiters there, if you were to track this over the surface of the Earth, the orbit sort of looks like, well, I'm not going to draw this correctly, but it looks like this, right? And it sort of hangs out because it's sort of turning from going, I guess, north to south. Not really the way to say it in orbit, but it gets a little bit more time where it's sort of like flying over those specific high and low latitudes. And then when it crosses the equator, it's moving a little bit more quickly as it goes down towards that part of the orbit. So it's not a polar orbit like this that would go, that is the worst. That would not be a stable orbit I just drew. But it's not polar, and it doesn't go over the north and south pole directly. It does have like a maximum and minimum latitude because of its orbit. Yes, JPL scientists?
That was very good drawing.
Okay, thanks. Whew. Okay.
Even with the crazy polar orbit, I think that was impressive.
There's probably like a name for that orbit, like the Moldnyaya orbit or something, where it does all sorts of random loop-de-loops, it seems.
The Galloway orbit.
The Galloway orbit.
There we go.
It is not a very stable orbit, let me tell you that much. Let's see, just a few more questions here. We're talking about orbits. Somebody said, well, the way the SWOTs work, if you put it in a higher orbit, couldn't it see more in each swath and get more coverage? So are y'all sort of going for the Goldilocks altitude there, where it's not too high and it's not too low, it's just right for Karen?
Yep. Yeah. You put that very well. Yeah, there's a number of considerations that go into this. So the tides actually in the ocean are a big driver of our repeat orbit. So if with whatever repeat orbit and how frequently you sample parts of the ocean, you could alias tides into your measurement. So tides obviously are very regular things, happen day to day, but also over periods of months and years. So if you sample those in just the right way, that you're aliasing them in and you're like just folding it into your observation in a way that it's very difficult to correct, that becomes a problem. But then, so that's one element that helps you select the repeat orbit. But just also where you're trying to focus on is sample most often to meet your science requirements. I mean, that's a lot of times what drives that repeat orbit. So, yeah, I think those are kind of the answers. There's a lot that goes into it.
Yeah. I've done that in Kerbal, and if you have like the lower orbit, you can get more resolution, but not as much coverage. And if you go to the higher orbit, you can get more coverage, but less resolution. And you're sort of like, the instrument is designed to work in this sort of space, and it's not just, well, put it at the moon and measure the entire Earth at once. Like, if it worked that way, you might be able to do it, but it would be a lot lower resolution. Whereas you get these sort of, I'm going to say, smaller SWOTs. That's not even the right way to say it, right? Because these are larger measurement areas than the point altimeters you were talking about. But it gives you these larger SWOTs, and then you wind it around and around the Earth, and you eventually get that whole picture.
Exactly.
It's a good question, though. Like, we start talking about a topic, and then I see questions about that topic sort of pop up over here. Some people are talking about how they would design a constellation of SWOTs, like what altitude and how they would be spaced out, and would they be like in a string, or I mean, that's the sort of discussion that's happening in chat over here right now. It's very cool. Let's see here. Do y'all want to compare SWOT data to GRACE gravity data? I'm telling you, we get all sorts of types of people into the chat over here.
Yeah,
we love GRACE at JPL for sure. Go ahead, Ben.
Yeah,
I was going to say there's actually a pretty good connection point between those. And if we think about California in particular, right? So we've had, I guess, a little bit less of a drought now, but over the past decade or so, we've had a drought here, and it's actually caused subsidence or a shift in the amount of water that's stored under the underground here in California. So there's been more pumping, less recharge that's happened. So you can see it in subsidence. So the land is sinking. So there's a set of satellites that can measure that. But GRACE is measuring gravity changes and can measure changes in water mass here on Earth. So it can actually see that part of it, what's happening subsurface. SWOT can see what's happening on the surface, but both tell us a whole bunch about where water is at any given time here on Earth, how it's moving around, and really what water is available to us. So you can kind of think of these as a constellation of satellites. All the pieces fit together, and some of the most interesting science comes out when you start looking at comparing GRACE Follow-On to potentially SWOT and to other altimeters. So it's a really good question, kind of cutting edge research that's being done with that kind of work.
Yeah, that's like literally a thing. It's like, oh, there's a little bit more gravity here. There must be more mass underneath this part of the Earth. And if it varies over time, like more quickly than geologic formations would happen, it could be groundwater, like literally the mass of the water that's underground that's causing gravity to be a little bit higher there. Minuscule variations in gravity. It's not like next time you step on the scale, be like, geez, the groundwater's high today. That's not how it works, y'all.
GRACE and GRACE Follow-On are incredible. So we could spend multiple hours talking about, or people who work on GRACE Follow-On could spend multiple hours talking about that. But it's amazing. It's
amazing what some of our scientific instruments can measure. Like doesn't the VLA like measure continental bounce or something like that? It's on the tour when you go on the tour.
No, the Very Long Baseline Array.
Whichever one.
It's 10 antennas from Hawaii to the Virgin Islands, and they're such precisely known locations that they can measure plate tectonics by the motion of those antennas.
It's crazy,
so
the things.
Study everything from the farthest reaches of the universe to the ground beneath your feet.
It's just so many things work that way. Like, we've designed this one thing, but look at this other little interesting bit that we found. Like, what causes that? Oh, well, we can use it for this. It's amazing the things that we're able to accomplish when we put together missions like this.
So actually, Joss, that was my one sort of last question I wanted to ask, which was, it's because it's one of those things that you can't necessarily foresee, but could you have a guess at maybe some weird way in which some people or interest group might use SWOT data that's different from what the plan is? My only guess right now is just that a 3-year record of some offshore surfing locations might be really nerdy for some of the surfers because they like that data. and maybe they discover a new wave that was like offshore somewhere. But
new early adopters.
yeah, do you have any other guesses? I don't know.
I think you probably hit on mine. I mean, again, I'm as someone working on sea level and coastal flooding, I'm drawn to what we're to find out about the coast, and it's such an unprecedented observation that I think there's just going to be so many different stakeholders. We're already talking to the military a little bit about potential applications of the SWOT data, how it might be useful for them, but it's not just going to tell us about climate change. I think it's just going to tell us about how water is moving in these coastal zones, be useful for surfers, be useful for really anyone who has some stake in that coastal area, which is a huge part of the population here on Earth. So I'm really excited to kind of tap into those and see what's there and then what you can infer from it. So a little bit of unknown, but an exciting type of unknown, I think.
Yeah.
Yeah, I would just say that, yeah, the coastal zone is something that we just don't have, the coastal ocean, we just don't have good information. And so I think we're all very excited to see what SWOT will provide there. But also, you mentioned GRACE and GRACE's follow-on. When GRACE was first launched, they had no idea about the kind of science and applications that were going to be coming from GRACE. And now, as Ben indicated, there are studies that involve both GRACE and the altimetry missions that that combination just makes the science and sort of the outcome even more powerful. And so I we're all very excited to see SWOT has some very specific science objectives, and we're just very excited to see how that grows over time as we learn more about the data and what it can provide, and we get these clever postdocs in and that grow up with the data and just start doing some amazing work.
Gotcha. I worry at times about saying that we're excited about, we don't necessarily know what we're going to learn and we're excited about that. Sometimes people may think, oh, they don't know what they're doing, but right. I think in reality, we're going to have these core science objectives, but then it's all that additional stuff that comes on top of it that I think is really exciting on the science and application side.
Yeah. It's just, go ahead, Margaret.
That was Summer.
With me, I just
Summer, sorry. It really is the way that it sort of works. Like, we talk about you don't know what you don't know in terms of, oh, I've built something, is it going to work or not sometimes? But it also works with learning new things about science. We go up there and we get some new data and we might notice something in the data like, wow, what's causing that? Let's look into this a little bit more. And it may open up entire new avenues of conjecture or science or whatever you want to say. Study is probably the right terminology. That's how we work. We don't know everything, and we build these tools and we come up with these ideas, and we go out and we learn about the Earth and we learn about ourselves. We learn about everything. It's literally what we do. And every time we learn something, it doesn't mean that now we know everything. It means that now we know more things that we're interested in, and let's go study those as well. It's really cool what y'all do.
Yeah.
We're just about out of time. There's always that sort of like last question that comes in, but I want to give you all an opportunity. Is there anything we haven't talked about? Something that's cool about SWOT or cool about the science that y'all do that you want to cover here at the very end of the show? Last time I started with Margaret, so let's start with Ben this time. Anything that we didn't talk about that you want to mention really quickly?
Yeah, nothing that we haven't talked about, but maybe the big key point here is just the fact that we're measuring all surface water here on Earth, right? With one mission. It's not focused on the ocean, it's not focused on land. We're able to see everything all at once with SWOT. I think that the potential there, in terms of what it'll tell us about just how water is moving about on Earth. I mean, water, we talked about some of the stakeholders, but anyone who cares about water is really going to have some kind of interest in the data that SWOT collects. So I don't want to kind of lose that bigger focus that SWOT's going to provide by talking about some of the specifics which we covered here. It's just really an unprecedented look and something NASA can do very uniquely with our satellites, provide that global view. So yeah, just maybe reiterating what I'm excited about with my last comment.
Yeah, absolutely. Margaret, how about you?
Well, no, just, along those lines, along, that thread, it's really just what SWOT's going to be able to provide, not only for science, but for, for decision makers and for you and me and everybody, it's just going to be really another tool in NASA's belt to understand the Earth system and how everything works together, specifically in the realm of water for SWOT. So that SWOT is all about the water. So.
It's all about the water. I like it. It's right there in the name. It's like surface water. It's like the second word in the acronym. If you can figure out what the SWOT team is working on. I was really resisting the urge to call y'all the SWAT team. Different type of thing there. But it really is something. I want to make a note real quick. Like, so many people watch live streams, and you watch rocket launches, and you see all this, this exciting things, right? That point in time in the mission where the rocket's taking off. We didn't even play the rocket takeoff on the stream today, but a lot of times people get so hyped up in that one moment of the rocket launching, they forget about all the work that goes before the rocket launch in designing the mission and designing the satellite and all the work that continues after the rocket launch. Like, the rocket launch is not there to entertain us. The rocket launch is a specific thing to get this piece of equipment or person that we've built or sending somewhere into the place that we want it to be. And we just don't focus on all the work before and afterwards. So from the folks at NASA JPL who joined us today, Margaret and Ben, thank you so much for all the work you do, the amazing science you work on, and everything that you spend your time on that makes us have a reason to see those awesome rocket launches sending missions like yours up into space. Thank you so much for the time today. We really do appreciate y'all taking time on your Sunday.
Oh, absolutely. My pleasure.
All right. As well, Summer Ash, a pleasure hanging out with you today.
Always a pleasure. And I love me some water, especially now that I live in the desert. So this was cool to talk about.
You live in the desert. Folks, that is going to bring us to the end of our show today. Remember, the Astro Live shows with the Intrepid Museum are supported through the NASA Cooperative Agreement awarded to the New York Space Grants Consortium. We're going to have another show next month, but next month's Astro Live is actually going to be Sunday, February 19th. I'm going to be at the Intrepid Museum in person. It's Kids Week, where they have all sorts of different, there's actually going to be NASA folks there, booths on the Hangar 3 area where you can go up and talk to the scientists, and they'll show you the demonstrations of stuff that they're working on, different guest speakers and stuff like that. We're going to have Mike Massimino apparently is going to be out there. Jessica Watkins, we talked about that or before the show, I guess. Jessica Watkins is going to be there talking about her experiences in time and space. Mike Massimino is going to be hanging out with her. We're going to be streaming that here on the same channel. That's next month's Intrepid Museum Astro Live. Next month, Astro Live. Yeah, we changed the name. I got to make sure that I think about it. Make sure you visit the website, intrepidmuseum.org. You can find out more information about visiting in person or how you can watch those live streams if you can't make it to New York in person. But that is the end of our show today. Thank you so much once again, Margaret, Ben, and Summer, for spending time with us. If you're watching the NASA Spaceflight channel, we're not done, because SpaceX is launching a Falcon Heavy mission for the Space Force. We are covering that. The stream should be starting right now. The back channel, the other folks in the production told me that they're live over there. So when we're done here, we're going to go straight over to Falcon Heavy launching out from the Cape. One more time, thank y'all so much for taking time out of your afternoon, after your weekend here, to spend with us and share us about information about the SWOT mission. But we will see y'all later. Thanks for watching, everybody at home. We can wave, and then I'll press the button that stops the stream.